So where do you usually stand?
Anywhere.
Anywhere, okay.
Yes, I think there is a camera looking more or less in this area, but you
okay.
don't feel obliged.
Okay, yeah. Okay, so hi everyone, I'm Changjae from Queen Mary. We are located just one station far from the Stratford station. So today I'll be talking about my group's recent work on robotic perception, especially vision-based robotic perception and manipulation through vision and also some text prompt or language. Just let me briefly introduce myself. So I studied in South Korea, and then I came here to Queen Mary as a postdoc in 2018. So I used to work on image processing and computer vision before. And then I joined some robotics project, and then I found some opportunity that vision can make some contributions in this robotics research. And I think obviously these days it's becoming more and more popular, and this is why I think this this program has been made in UCL. So I have some postdocs and some groups, and so I started to be more dedicated to some robotics society. So we are running some competition, which I will advertise later on in the important robotics conference, and also we have some workshops. So my research interest in one line can be just described as embodied agents' perception and action through vision and language. So for example, let's say we have this kind of robotic environment where the object that we want to manipulate is placed on the table, and then there's a robot arm where the camera is attached to at the tip of this robot arm. And then through this camera, then now this robot can receive this image, right? And this image, let's say this one is just 100 by 100 size image, then actually this is very redundant and meaningless itself, because this one is just a bunch of integer values. For example, if it is 100 by 100 images, and then there are 30K pixel values, considering this is RGB image. So then this image is passed to this encoder so that we can extract some useful information rather than just keeping all the 30K integer values or floating point values, which is called feature. And then we use the feature as input for this actor module or actor to perform some desirable actions, which can perform some target manipulation tests. So basically, also this kind of thing can be performed with vision or vision and language or text prompt to give some more specific guide what kind of manipulation task we want the robot to execute. So in my group, we are interested in some research challenges that might have arise in this pipeline. For example, some encoder might some research problems, or actor part might have some research problems, or this environment may have some research problems as well. Okay, so this is something that we have done so far for the last few years. So at the beginning, I used to focus more on the computer vision part. So as far as I understand, I just roughly went through your module list. And have you ever really taken the real computer vision module, or not really, right? Just deep learning and some reinforcement learning, but it was not the... Okay, then I'll try to explain more about some details. So first, we used to work on some 60 pose estimation. So here the 60 pose is let's say, we want to let the robot or machine to understand where the object is placed in this 3D world with what kind of pose. So 60 pose means that we would like to understand about the XYZ location or the translation of this object in the 3D world, and also the rotation, how this object, based on the reference view, has been rotated with respect to the x-axis and the y-axis and the z-axis. If we can have some understanding of this 60 pose, then it means that now robot understand where this object is placed and how. And then we can execute this kind of object grasping. And then we are also interested in doing some human-to-robot handover task. So this human-to-robot handover task might look relatively simple, but at the same time, what you can see here is that actually we are dealing with some dynamic environment, because the human is delivering the object to a robot, and then we would like to ideally let the robot to grasp this object while not harming the human hand. So in this environment, we did some research about 3D hand object shape estimation to understand how the hand really look like in 3D world, and also how the object looks like. And then these days we are working on something related to realistic rendering, and this one can be slightly related to the world model, and I will talk more about this realistic rendering. And also we have been working on some vision language model based fine-tuning or pre-training so that we can perform diverse tests such as pick and place or some other 3D robot manipulation test. So today I will mainly talk about what we have done in this for the realistic rendering for human to robot handover, and VLM fine-tuning and VLM pre-training for robot manipulation. Okay, so generalization ability in this robotic perception and manipulation, we can just describe it as the model's capacity to execute diverse manipulation tasks on a new and unseen data. So ideally what we want to have is this kind of model. Let's say the model has been trained, the encoder and actor has been already trained, and we fix this parameter. Then if this model has very nice ideal generalization capability, then what we would like to do is we would like to let this model to perform any kind of robotic task in any environment with any kind of different action space, which is currently impossible, and this is why people are working towards the generalization of the robot, and also why we are doing some robot learning. Yeah, so today I will go through 3 different topics that we have done last year. And yeah, we try to address try to answer to the 3 research questions. The first one is, can we train a robot to learn how to move without moving the robot? The reason that we chose this topic is because also me and also my students' research background is more like computer vision side. So we still feel scared to move the real robot because it breaks down and also it delays our research quite a lot. So we started to think about if there is any way for us to use some simulation environment or some realistically reconstructed environment to perform some robot learning, and then just simply transfer that model to the real world so that we don't have to really move the robot during training. And the second one is, can we train a robot to learn from a few robot demonstrations? So it is always good to give some demonstration to the robot so that we can use this demonstration to further fine-tune the robot and then perform some robotic task nicely. And the next one is, can we train a robot to learn better representations for robotic environment? So usually we use some model already pre-trained for the computer vision task. And just one limitation of those models is they may not have good understanding of the robotic environment or some instruction to do some robot manipulation. So we did some work to train the model from scratch to equip with the better representation for robotic environments. So these 3 will be the main topics that I would like to introduce. Mainly what I will do is, for each topic I will try to introduce about some motivation, why we wanted to work on this topic and what's the limitation of the existing method, and then some backgrounds to help you understand our work better. And then I will talk about the proposed method, and then validation in the real world, real robot environment, and also the simulation environment. But before we move on to these 3 topics, I would like to go through some very fundamental skills for robots to interact with the real world. Okay, so this is the pipeline that I have shown you, that I show you at the beginning of today's lecture. And here, yeah, it looks quite convincing, but at the same time, if we just see one by one, then we actually don't know how this action looks like. And then this one, we are receiving image. Image is 2D, and this is just the image. And then here now, the robot is moving in 3D world. So let's just roughly go through how is this kind of action can be defined, and how we can link this image to the 3D world, and how we can move a robot arm. So probably you have learned some of this, so it would be a good chance for you to just simply review what kind of fundamental skills or concepts are required for us to really move the robot in the real world. Okay, so let's say we have this kind of robot model, and then here the action can be defined in a sort of diverse manners, and with different action space, based on the application or mainly based on the applications, for example. So for example, let's say we want to perform some human to robot handover task, and then we have some good perception, and maybe we may just want to have some this model to generate the XYZ coordinate, 3D space, and what we just need is the object centroid, and then in the 3D space, and then we can just let this model to move this robot arm to move towards this XYZ coordinate, and you have learned about inverse kinematics. Another one is rotation and translation. So here the robot gripper is fixed. But if we want to also change this robot gripper to have a better degree of freedom to execute the grasping, in this case, then we may want this model to generate the action that consists of the rotation to the X and Y and Z axis, and the translation, which is related to this XYZ coordinate. Then based on this information, if we can generate this action, then we can perform the robot, human to robot handover or object grasping more in a higher degree of freedom. And what about pick and place task? So pick and place task, we usually use the camera at the tip of the gripper. So we are looking from top to bottom. So assuming that we already have some depth information, or we have a depth sensor attached to this camera, then actually this problem becomes just a 2D problem. What we need to do is we just need to find the location of this gripper where to grasp in 2D space, because this one is just top to bottom, and the angle of this gripper. So in this case, then we just want the model to generate the action, which is XY coordinate in the image and the rotation angle of the gripper. And the most generalized version of this kind of robot action can be the joint angle. So when this robot arm is moving, actually robot arm is moving by adjusting the joint angle of the robot arm, right? Yeah, so in this case, then we may want to let the robot, this model to generate this kind of joint angles. Yeah, so as you can see, there are diverse ways to represent the action space. It can be really based on what kind of robot manipulation task we want to kind of perform. And the next concept is camera calibration. Anyone know camera calibration? Yeah, just probably. Oh, wow. Yeah, so camera calibration, so here the goal is to kind of find some relationship between the image space and the camera space and the 3D world space. When I use a camera to take a photo of you guys, and then this one, I will lose a bunch of 3D information, and then it will be just stored in a 2D image space. This 3D world can be presented with some kind of physical length or width, for example. But after we take a picture, then it just becomes the pixel space. So there are some way, which is called calibration, to find a relationship between this 3D world and the camera space and the image space. So and after we do this one, and then Augusto is here, and then what we can do is, if there is any perception and also some information, then we can even transfer this information to the simulation environment, because we know how this object is far from the camera. Yeah, and also we can reconstruct the environment in the simulator, and then we can also further use the simulator to complete some other task for simulation. Yeah, and just one example about camera calibration. So this is our lab, and here what you can see is there are some sort of checkerboard. And we already know the width or the length of the square. Let's say this one is 15 centimeter, and then let's say this one is like 5 centimeter each. And then in this 3D world, let's just assume this one is a 3D world. Then we can somehow define this point as a 0, 0, 0. And then this one is just 15 centimeter far to the y direction, let's say. Then we can consider this one as 0, 0, 0, and this one is 0, 15 centimeter, 0. And then we can also apply, obtain some coordinate based on the ratio or the length of or the width of this one to obtain the corner point 3D, let's say, coordinate. After we obtain the 3D world coordinate, then what we can also do is we can obtain the actual pixel coordinate to the point of this point. Because this is an image. And if you just simply put your cursor here, then you can easily obtain the XY coordinate to the point, to the coordinate of this corner, right? So by using this information, the points information obtained from the 3D world and the points information obtained from some 2D image and with some camera parameters, then what we can do is called calibration that estimates some parameters to find the relationship between the 3D world and 2D world, 2D image. So by using this information, then what we can do is, there are slightly a gap, but still what we can do is, let's say we want to find the centroid of this cup. So here now we have the 2D point, 2D centroid point, 2D centroid of this cup. And then using some information and of this calibration parameters, then what we can ultimately obtain is the 3D world coordinate of this object centroid. Which means that now this robot or machine has some understanding of where this object is located in 3D. Yeah, so in this case, we have, let's say, vision perception that allows a robot to recognize the object to grasp. And let's say we have a calibration parameters that allow a robot to understand where the object is in 3D space. Then we just need one more fundamental concept or skill to let the robot grasp this object. Anyone? How can a robot physically reach the object, and what is the core concept? Yeah? Yes, inverse kinematics. And you guys know more than me about this one. Yeah, I don't know very much. I just use this one as a tool. But yeah, just here, what we know is that we need to calculate the angles of joints that will cause the end effector of a robotic arm to reach some desired point X, Y, Z in 3D space. So after we obtain this 3D point, then what we need is just, we need to use this inverse kinematics to let the robot arm to reach to this X, Y, Z coordinate. So by using this kind of fundamental skills, now we can say that we can finally interact, our robot can interact with the real world. Yeah, so by just simply combining this information, then object centroid, after we obtain object centroid, and then using calibration parameters, then we know where this object centroid is located in XYZ point, and then we apply inverse kinematics to execute the grasping. Yeah, so these are the fundamental skills. Just wanted to, just let you know, because probably you might have some expertise in this inverse kinematics, but you might not have heard about the calibration, which is actually very important and very, if you actually implement this one, then you will see how disappointing the performance is. And then usually mainly the interaction, the real robot interaction fails because of this calibration quite often. Okay, so let's move on about the three topics that I would like to mainly introduce. The first topic is, can we train a robot to learn how to move without moving the robot? Okay, so let me just first introduce some motivations about this topic and some observation why we started to work on this topic. Okay, so this is the robot training in the real environment, and then here now we are dealing with the human to robot handover. Human is giving an object to a robot, and then robot should be able to execute the grasping successfully, and then put this object to the desired location. If we train the robot or perform robot learning in the real environment, good thing is that it is the realistic. It's a real, actually, environment. And it can be robust and accurate as long as we collect a bunch of data. But the problem is that it is expensive to collect a lot of data set to let the model to have good generalization capability. And also it might be unsafe if there is a human involved in this robotic task. If it is just a pick and place test, it might be okay, but just imagine that you need to do this one with the fast moving robot, and humans should give the object to a robot. And then we need to repeat this one for 1,000 times or 10,000 times. yeah, it would be quite difficult. And simulation, yeah, it's safe. And we can reset the environment as much as we can, and it's very safe, and it can be parallelized. So it can be cost effective in terms of the data collection. But obviously what you can see by comparing this one and this one is, here you can see that there's a domain gap. So this is the real environment, and this one is the simulation environment. So even though we can really perform a lot of training and learning in this simulator, sometimes it's very disappointing because if you simply transfer this model to the real world and then you fail. So what we wanted to do is, because this paper was actually sort of the following up paper of what I did with my student in 2019. But let's have a look at this image or video. So here, this one is the hand-eye robot on motion in the real world. So we have a robot gripper, and then we put the camera at the tip of this robot arm. Then we execute the human to robot handover. And this is the view that the robot will see. And the next one is the virtual camera motion in 3D scene. So have you ever heard about NERF or Gaussian splatting? Anyone? Yes. So this one is, so you have the multi-view, and then based on that multiple view, then you can roughly reconstruct the 3D environment of the scene. And then what we can do is, after we reconstruct this 3D environment, and then we can just simply change the virtual camera position, and then we can obtain some image like this, the sequence of images like this. Then we started to think about if there's any way for us to use this reconstructed 3D scene. Of course, the quality is not as good as what we wanted to have, but this can be really improved because these days the model is becoming better and better. The computer vision model is becoming better. So we wanted to mimic this environment so that we can do some robot learning in this 3D environment, 3D reconstructed scene, and then just simply transfer this model to the real world. So in this case, then, we can just collect the demonstration data and train the handover model in the reconstructed scene, which might be better than using simulated environment, which you see here. So we don't have to do the real data collection, and also we don't have to really move the real robot. We can just simply change the camera pose in this reconstructed 3D environment, and we will be able to obtain a bunch of data. And then we can just simply deploy the train handover task policy model in the real world directly. This was our concept of this paper. Okay, so the approach. So first we perform some Gaussian splatting-based 3D scene reconstruction. So there are some public benchmark called DexYCB data set in this research field, or some 3D hand object shape estimation field. And then they provide some multi-view images. Then based on that images, then we reconstructed this scene in 3D. And then what we did, it was just we generated some demonstration in this 3D environment. And so this one is, let's say this one is the gripper pose, and then we can obtain the image from this each pose, because you can just consider this one as a camera pose. And then we can obtain the image for each camera pose and the starting point, and there are some grasping image. And then we can obtain some segmentation mask and some information about some transition and whether the object is now somehow grasped or not. Then we collected this data set, and then we trained our model that used only the input image and the segmentation mask of the hand and object. And then we trained the action policy to perform the reaching and the grasping task. So we have RGB, and we know where the hand is, we know where the object is. Based on this information, this policy should be able to approach towards the object. And then if it is close enough, then this kind of, let's say, classification result will determine that we have reached to the pre-grasp pose. And then we just give some kind of extra, let's say, 5 centimeter approach just to straight to execute some grasping. Yeah, so first we validated our model. After training, then we validated our model in the simulation environment. So this is just a 3D scene reconstruction environment. So we just deployed our model in this 3D environment. So the left one is a scene objects during training. The right one is unseen objects. Then here what you can see is then this action policy model can somehow generate sort of the motion or the trajectory that looked like we are now reaching towards the object. Then we were a bit confident that maybe we can now transfer this model to the real environment. Then we transferred this model or deployed this model directly to the real environment without any fine-tuning or training or further training. And then we could somehow successfully reach to the object and then execute the grasping. Of course, this is very sort of the first work of my first year PhD students. So as you can see, the robot motion is very slow and still there is a large room for improvement. Yeah, but still what we could validate here was that we can do some robot learning without moving the real robot. Yeah, so itself was quite meaningful, and now we are trying to improve this reconstruction scene using some generative model and then do some further robot learning in this reconstructed domain to do some more complicated task. Okay, so this part we would say somehow it can be one kind of word model. So of course the quality is very poor because if you just think about the word models, you might have heard about word models, right? Yeah. So this one uses input data like text and image and video and movement, and then the word model generates videos that simulate the realistic physical environment. So these are some the work from some other paper, which is all generated. So if you see those videos carefully, then you can see actually there's no actual grasping happening, and also the image changes a little bit. Yeah, but somehow similar. So we were quite excited to have this kind of initial work, and now we are extending our work. Yeah, and so for those who are interested in doing some human-to-robot handover works, and then if you have any chance to attend any competition or conference in this ICRA, and then we are arranging this competition in ICRA in Vienna, and so you can discuss with your supervisor and then think about attending this handover competition. It will be relatively less competitive, but also you will be able to get a good score. And the topic itself is, I would say, quite interesting. Okay, and the next one is, can we train a robot to learn from a few robot demonstrations? Yeah, so here what we want to do is we want to use some few demonstrations. And before we move on, so I'll also try to cover a bit about some computer vision-ish concepts. So have you heard about CLIP, right? Okay. Yeah, so Vision Language Foundation models, or CLIP, learns to align images and text by training a pair of neural network on internet scale data set. So we have this image encoder and text encoder. OpenAI released this CLIP model. And then what they did was just they have a bunch of images also have corresponding annotation, text annotations. And then they just trained this model to have a similar feature, image feature and the text feature, as long as they come from the same class and image. If this image and if we have a text prompt associated with this image, then this text feature and the image feature should be close, while other features should be far away or not as similar as these two. After the model is trained with internet scale data set with large parameters, then what we can do is now this CLIP model itself can be considered as a classifier because it is already generalizable enough. For example, let's say we have an image where this model has never seen. And then we can obtain this image feature. And there are some kind of candidates of class that we want to perform the classification. And we give a bunch of text input here. A photo of a plane, car, dog, bird separately. And then we obtain all text feature. And as this model has been trained on a very large scale data set, so in this case, then the similarity between this image feature and the text feature from a photo of a dog will have the high similarity. By using this information, then we can perform the classification. So this is how this CLIP model has been used for computer vision tasks in the for the classification. And there was another, then we started to think about, can the CLIP model improve its generalizability on the robotic task? Because this CLIP model itself was trained on the internet scale data set. But actually, if you see the text prompt carefully, then this one is slightly different from what we would like to give as input for the robot manipulation. So compared with the robot instruction, then this might be a bit different. And another one is internet scale images might be quite different from the robotics environment that we want to perform some manipulation. So yeah, we wanted to fine tune of just a few parameters, because if it's impossible for us to really fully train this model. We wanted to fine tune the few parameters and also using some few shot demonstrations. And the next concept is called concept fusion. The CLIP model performed classification, and this model, together with some other foundation models called like segment anything or some segmentation methods, then this model enabled to perform a bit more fine-grained task, or let's say image localization. So I can just skip this part, but here what you can see is there is a segmentation, and then you can extract a bunch of local images, and then you use some text information. Then unlike just using the CLIP model for classification, in this concept fusion model, what you can do is, if you give a text prompt, a photo of a yogurt, and then what you can obtain here is that you can highlight where this yogurt is. So it can be considered as an object detection, but actually it can be considered as an image object localization task. So Diet Coke, then we can also, let the model understand that where the Diet Coke is. So it means that now, if we can somehow use this CLIP model, then we can now let the robot understand where this object we want to manipulate is, and then we can execute the grasping or pick and place. And another one is, so some ideas we borrowed from the natural language processing. So in natural language processing, there was a paper about sort of fine-tuning this CLIP model, because also they found that this CLIP model is very good. I mean, generally it's very good, but also at the same time, they may want to just fine-tune a few layers so that they can have a better performance while keeping the generalization capability, which is called zero-shot performance. And then they have found that just fine-tuning a few layers of this layer norm or bias, and then they can obtain a good performance, still keep the zero-shot performance or generalizable performance, but much better than the vanilla CLIP. So we combine all these things. Also, somehow it's just a combination, but also it's very good work, because this is the work from the first-year PhD student. So given the observation, and then we designed some complicated pipeline, which I wouldn't like to go through. And so here what we did was, we used some few shot demonstrations, and then by using those demonstrations, then we did perform some selective fine-tuning. We just selectively fine-tuned a few parameters, which is just 1% of the trainable parameters of existing models or other baselines. And then also decompose the picking and placing task. And by using all this information, then we could somehow come up with a nice few-shot based pick and place solution. So these are some scene objects. You can see there are some pick and place can be done relatively successfully. But also the important thing is we can also deal with some unseen objects. The reason that we can deal with this kind of unseen objects is because we fine-tune the CLIP model, but we selectively fine-tune a few parameters to let this CLIP model to be adapted to the robotic environment while keeping some zero-shot performance or the generalizable performance in terms of, let's say, classification or object understanding or scene recognition, object recognition. And also some meaningful results that we have got here was this one. So compare with some existing baselines that when we were presenting this, preparing this paper. So here what we could see is that thanks to the sort of the capability of this kind of clip model and also few layers training, fine tuning. When we just simply use one demonstration, then we could see that our method could perform much better than the existing model because we still can bring the generalizability of the clip model. Of course, yeah, so in this case, the reason that we could work on this one was because we use many different foundation models, clip and also segment anything, which perform very nicely and generally performs very well in terms of the segmentation, but sometimes it is not enough. And this is, anyway, as long as we are playing with this kind of foundation model from the large company, and then upper bound is the performance of the model. Of course, it is good enough, but still it shows some bad performance. So for example, here we want to segment the blue ring, which is here. And it is very difficult for this segmentation method to really segment this part successfully, given this text prompt. And also here, this is what we want to do is we want to pick up the lightest brown blob, let's say. Then we want to segment only this part. But if this one is not successful, then the following robot pick and place test will be also unsuccessful. Okay, then the last one. Yeah, the last one is, can we train a robot to learn better representations for robot environments? So we did a few shot training here. Then we just decided to move on to the full training. And have you heard about self-supervised learning in computer? Anyone? Okay, so someone who studied, I think, computer vision know about this topic. Okay, so self-supervised learning methods solve, let's say, pre-text task that produce good features for downstream tasks. So here the pre-text task is some task that is not our direct interest, but this can be related to for the model to further perform some target application task. So for example, here, image completion or rotation prediction and jigsaw puzzle, doing some puzzle and the colorization. All this kind of task, one advantage of this task is that we only need an input image. Just by simply manipulate the image, the input image, we can just simply erase the upper part and then we can let the model to complete this remaining part. Or we can just simply rotate the image and then we can let the model to predict how much this object, this image has been rotated. And also we can let the arrangement of this patches and let the model guess the arrangement or the order of these patches. And also we can just let the deep learning model to give some nice color, reasonable color to this object. And all these things can be just done by using input image, by simply manipulating the input image. There's no human annotated label. We can just simply delete, rotate, or just rearrange the patches and remove color as input image. And somehow, also there's another way, which is called masked autoencoder approach, which is sort of the extended version of this kind of image completion. Yeah. So here what you can see is that there are some empty patches of this image, and then we let this model to complete this image. So all these things can be considered as a self-supervised learning task. The reason that it is self-supervised learning is because there's no actual label that we annotated. We are just using this image, and then we generate the self-supervised label from this image, input image. Okay, so why are we doing this, and why is it necessary? So this is how the self-supervised learning approach can be used. We can obtain a bunch of unlabeled data. We can just simply crawl these images on the web, which is not that costly compared with some, let's say, some data that we need to really annotate, or where the human needs to annotate one by one. Then what we can do here is that first we can use this lots of unlabeled data to perform self-supervised learning of deep learning model. So here what you can see is we perform the rotation prediction task, which is actually not that relevant to classification or detection task, right? But by doing this one, then we can somehow obtain a nice representation or the nice first few layers that can extract some edge information or some cluster some information to come up with a nice answer for this one. And then what we can do is we can transfer this parameter for our actual task here as an initialization. And then we can fine-tune this model to perform a specific task like classification task or detection task using a small amount of labeled data. So this is the advantage of self-supervised learning. So we can first make the model smart enough to be adapted to any specific computer vision task or other task. So this was our motivation, and let me just introduce a bit more. So robot and robotics and robot learning. So there's a large amount of data we need to collect if we really want to perform the robot learning with just from scratch and then collect them. So this is what happened, like, when was it? 2018, 19? Yeah, that time Berkeley, they bought a bunch of robot arms and then they collected the data for pick and place. It's difficult. It's Stanford. Oh, yeah. They collected this data, but then there's one problem. So there are many problems, actually. One thing is that you cannot collect this data, right? We cannot collect it, or this amount of data. This one is just for pick and place. And just imagine that this one is for the human to robot handover then.
Is there a human doing that?
No. Yeah. But probably they first gave some imitation, some demonstration, and then they started to make some generalization or some perception. Yeah. So, and then here you obtain image and also some joint angles information. And another problem of this collecting the robot data is, so here you can see, so at the beginning, almost the early time of this lecture, we talk about the robot actions. So robot actions can be defined in a diverse manner, right? It can be X, Y, Z coordinate or rotation translation or X, Y to the point with rotation angle. And all those data, like action space, cannot be covered by the pre-collected data from Stanford, right? And also here what you can see is we have diverse robots, arms. Each one has different capability and different joint angles capability and the different number of joint angles. So even if they have collected several, let's say, joint angle information, some joint angle information through this data collection, this may not be transferable to other robot arms. So there are quite many problems here. Okay, so then let me try to just compare the pipeline that I introduced at the beginning of this lecture and the self-supervised learning and the supervised learning approach that I just introduced now. So if you see these two carefully, then there are some similarities. Of course, this one is robotics work and this one is computer vision work, you may think. But let me just try to convince you. So this one is an encoder. We have an input image and then we obtain the feature or the representation, right, for robotic task. And if you see this part, so this one, our ultimate goal of the self-supervised learning is to train this feature extractor, to let the feature extractor smart enough to perform the target task, right? Somehow this one and this one is similar. And this actor and this evaluate on the target task, or this part, this linear classifier part, can be somehow similar. Because here we obtain the representation that can be generally applicable to diverse robotic tasks. And here we obtain some representation that can be applicable to diverse computer vision tasks. And then we add some extra layer here to perform different recognition tasks. And here we also add some extra layers to come up with a target manipulation task. So here what we wanted to do is focus on this part. This part is different because based on the robot you use anyway, it will be changed. So we started to think about, shall we do something like self-supervised learning for us to improve the representation power of this robot model. And there was one paper called Croco. It's called cross-view completion. So this one is a self-supervised pre-training method based on the cross-view completion. So here what they do is they have multi-view images. And then they mask some part of this view, and then they have a reference view. And this one has some overlap. Based on this overlap, then they just let the model train to fill in this masked region. And why then? So this is also another kind of self-supervised learning approach, but designed more for the 3D computer vision task. Yeah. And they found that this one is very suitable for the 3D vision task. So motivated from the self-supervised learning that I introduced, and also some self-supervised learning through this multiple view, then what we started to think about is, can we also learn the causality of visual state transitions in language-guided manipulation? So complicated, but if you see this one, this is what we wanted to do. So we have some video clip, also there is some textual annotation, and then we wanted to make use of this one to come up with a better representation for the robot. Or we wanted to improve our encoder to be adapted to the robot environment. So we have text prompt, and we have input image, and we can also obtain the masked image, the goal image. Now we just give the mask of this goal image, and we let our model to predict how this goal image would look like if we put the red object into the pod. As we already have a video clip and its associated robot instruction, then we can design this kind of self-supervised learning approach to make our robot, this encoder, to be smart enough to adapt to the various robotic tasks. So after we adapted this one I'll talk a bit more about the methodology of this LavaMan. And then this one has been also adapted to, so after we perform this one, then we use this representation and then add extra head, or let's say actor part, to perform diverse robotic tasks, which can be validated in the pick and place in the simulator, or real robot, or some different 3D manipulation that actually considers action as a joint angles of the robot arm, or some computer vision test called referring expression grounding, which detects the object in the scene. Yeah, so this was the main approach of our method. So this dataset is already given. There is a short video clip and its associated textual input. And then here we just simply pick the first image and the last image of this video clip and its textual input. And then we gave the masked goal image as a hint, because if we don't give this hint, then it is quite difficult for the robot, this model, to really understand what they have to predict and how the final goal image would look like. So we gave this hint, masked goal, and then we let the model to just simply perform the goal image prediction. After this goal image prediction is successfully performed, then we use this representation to further adapt to the actual robotic task, as you can see here. And also extra benefit of this LavaMan model is because our model has some understanding of goal image prediction. And even though this is not very perfect, but if we use this one also as an input for robotic tests, then we have found that this one is quite useful to improve the pick and place or other robotic tasks. Yeah, so first we validated this one, our, let's say, model's performance in terms of the goal image prediction. So we have input image, and then we give this kind of textual comment. So fold close from top to center, fold close from right to center. Of course, this is not very perfect because, and also our goal is not to make this image to be perfect, but here what we want to understand is whether our model has some understanding of this textual comment. So close the drawer, then you can see this model can predict the image where the drawer is closed. Right? And also put the pink object into the drawer, and then you can see this pink object has been disappeared, right? And then somehow it's here. So now we can somehow validate, verify that our model has some understanding of goal image prediction given the textual comment. So we use this one for robotic tasks and various benchmarks, and then we could obtain some good results. Yeah, so here also one interesting thing that I would like to say is, so sort of by looking at this table, so this table shows just the results, bunch of results and numbers, and always we say ours is the best. But here what I would like to highlight is this kind of one. So we can also just train our model without pre-training, especially if it is just simulator. This one is the results on the simulation benchmark. So we can train our model without pre-training model. We can just train our model from scratch. Then it also shows some performance. And then here what we could have seen is that without pre-training, without having sort of strong representation that align with this robotic environment, then we could see that the performance may not be as good as other models. Of course, if we really have a bunch of data set, then this will be ultimately overfitted to that environment. But as you can see here, so yeah, some pre-trained methods usually outperform the no pre-training method. Yeah, so some more examples. So here we have this kind of top-down view. And based on this top-down view and assuming that we have access to the depth information, then so in this case, then we will just need x, y coordinate and the joint angle. Then we use some few demonstration to fine-tune the later part or the last layer that generates the action, and then we could perform the pick and place test relatively well. Yeah, so these are the 3 topics that we worked last year. So first one was, can we train a robot to learn how to move without moving the robot? And in this case, we proposed to use the 3D reconstruction and then try to imitate the robot movement in that reconstructed scene. And second one is to learn from a few robot demonstrations. So we use some foundation models and existing technologies to fine-tune the clay model, just a few layers of clay model to keep the generalization capability while still adapting to the robot environment. And the last one is, we propose a self-supervised pre-training approach to learn a better representation that can be adapted to diverse robotic tasks. Actually, we have extended this paper to a journal, and then we have seen that by using more data, and it performs much, much better. And also, it can perform more diverse tasks. And hopefully, I have some chance to advertise the work later if the paper is accepted. So now we are working on several more topics related to robot learning, and so those are not yet ready, but just would like to introduce what we are working on. So one thing is that probably you have been working on some reinforcement learning, right? And then usually reward signal is just 0 and 1, or there might be some intrinsic rewards. And then we are working on something to learn from better rewards for robot manipulation task. And the last paper, we just used the first image and the last image, which is the initial image and the goal image. So what we are actually doing now is that if there is any way for us to use this kind of intermediate frames, because by using the input image, first image and the last image, of course, we can obtain the initial state and the final state of this image. But at the same time, we can somehow use these intermediate images to let the model learn some temporal transitions of the robot or the temporal movements of the robot. So now we are extending our previous work to have the representation to have some temporal understanding, which might be useful for, let's say, more dynamic environment. And also vision language action model. Hopefully we're preparing some papers, and then previously some VLA models, they tend to use some explicit 3D perception models, and then they attach those kind of perception results to this vision language action model to perform robot manipulation task or some other task. And then now we are tackling those kind of approach, and then hopefully we can submit in a few weeks. And the last one is about the human-to-robot handover. So if you just think about the human-to-robot handover, what we wanted to do is we want to give some more room for adaptation that human can do. And what you can also obtain is human-to-robot handover. Actually, the most important part is when the grasping is happening, when this human-to-robot really happens. And also, if you see this moment carefully, and if you just simply look at this part, then you don't know whether this one is human-to-robot handover or robot-to-human handover, right? So what we want to do here is that we want to just focus on this moment. we can just let the robot gripper like this, and then we can just give bunch of the object pose. And then we can use this information so that human can give some feedback on where this object, where the robot should grasp. Yeah. Yeah, so we are using this, we are also working on these two, for this topic. And that's it. Yeah, so that's all from my side today, and thanks for listening to my presentation. Thank you.